We'll take an example to understand the stepwise logistic regression. I'm going to show you how to build a logistic regression using stepwise variable selection methodology. So we'll take a data set. So here is a data set which is the details of cancer patients, and they have undergone medications, and we need to predict what is the probability that somebody has been uh, completely free of cancer. Okay, and in medical terms we call that as complete remission. So if somebody is completely free of cancer, then we assign a value of 1, otherwise 0. And there are several factors that contribute towards this probability. Okay, so whether somebody is completely free of cancer depends on the 6 variables. Okay, and we'll build a model, a logistic regression model to find out what is the probability that a patient is free of cancer. Okay, so to do so, and you have seen in the data set that the variable of interest has value of 1 and 0. So in such a case, when we have only 2 values in the target variable, we cannot use a linear regression. We have to use a logistic regression or a probability regression. So we'll go ahead with a logistic regression. Okay, so in SAS we use the procedure logistic, and the syntax is pretty simple. I'll explain it to you. Proc logistic data, and then cancer, which is the name of the data set, and then we're going to get our statistics, model statistics in a data set, and that's where we're saving it as, we're calling it as betas. And then we'll define the model as this model, and the target variable is Ramesh. We'll write that in the left hand side, and then we put all the factors as the independent variables in the right hand side. Now here proc logistics by default it considers the lower value as the variable of, or the value of interest, but we are not interested to find out whether somebody has cancer. We rather are interested in knowing whether somebody do not have cancer, or somebody is free of cancer after medication. So we're interested is in predicting 1, not 0. So we have to mention this explicitly. Okay. Alright, so this is the basic syntax of logistic regression, and then we'll come to the stepwise. So I'll start with the basic syntax, basic logistic regression. So I'll remove the selection part, and then we'll run this first, and then we'll go over to selection. So this is the plain vanilla form of logistic regression, which has got only the model and no variable selection or no feature selection in place. Okay, so let's run this. So how do we interpret the results? So you can see in the result, the first thing we need to see is that whether it has converged or not. Okay, so we need to see the convergence status first, and here you can see the model convergence status, and you can see that the convergence status criteria has been satisfied. That means the result that is going to be followed is likely to be correct. Okay, if that's not satisfied, then you cannot explain the results that is going to come out of this estimation process. Okay, so there are few important statistics which are of interest to us. Model fit statistics, which is AIC, archaic information criteria, squash Bayesian criteria. Now these statistics are used to compare models. When you have similar models, a few of models, so the values AIC and SC are compared to see which one is the best model. Okay, and the lesser these values are, the better is the model. Okay, so since this is a single model, we won't get into the details of it, but while comparing we will make use of these values. Okay, and then testing for global null hypothesis. So the global null hypothesis says that whether your independent variables or the features, the 6 features that you have given as the input, are contributing towards finding out the probability of someone completely free of cancer or not. Okay, so global null hypothesis has the importance that if this is not satisfied, there's no point in going down and explaining things. And this seems to be satisfied because you can see that it is significant enough, so it's satisfied in this case. That means we are good to go with explaining our model results. The next in the result section is the analysis of maximum likelihood estimates. So logistic regression uses maximum likelihood estimation process to get the estimates, the point estimates. Okay, so, or rather we call that as beta parameters. We have the intercept and the slope, right? So we have got 6 independent variables and we have also got an intercept. Okay, so there are 7 parameters we have from the estimation process. So all you need to see is how many of these parameters are significant. So how do we check that? Well, we need to look at the p-values. If the p-value is less than 0.05, then we are sure that the variable is significant at 95% confidence. You can say only one value is significant, right? Or not even that. It seems that all the independent value seems to be not significant. Okay, and that's quite strange, right? And it happens because we have very less number of observation. We have only 27 observation which we have given. So if we find any kind of issue with this data, we might have some strange result. And this looks quite strange because none of the independent variables are significant. Okay, now we'll do an investigation into this. So before that, among the other thing that's important to us is looking at whether to what extent the model is doing good job. So for that we need to look at what is known as the C statistics, or we call that as concurrent statistics. So C statistics lies between 0 to 1 and it has to be always greater than 0.5. Otherwise there's no point in building a logistic regression model. Okay, so it most of the times lies between 0.5 to 1, and the closer it is to 1 the better is the model, and we have got a value of 0.88. That doesn't mean much, but we need that value to compare a model. Okay, so we will have several models in place through various techniques, and concurrent statistic is going to be useful while selecting the best model. Okay, so the one that we have seen is the basic form of logistic regression model, and what we have seen here is that there is some issue with this model because none of the independent variables are coming out to be significant. Okay, now oftentimes what happens is that some of the independent variables are not very important. In fact, they cause issues in the model. They cause the good variables. Some of the not so important variable cause the important variables to be not significant. Okay, so they affect the model adversely by making the good variable or the important variable insignificant. Okay, that we need to tackle. So we need to remove this unwanted variable or insignificant variables or not so good variables. So how do we do that? There are several selection techniques available. The popular ones are stepwise selection and forward selection, backward selection, and there is also another thing which is called subset selection, which we're not going to talk about it here, but we'll give a brief idea what subset selection is. Okay, so we'll use the first selection method that we're going to use is stepwise. So the same syntax except the fact that we're using a keyword selection and then we are using stepwise as the selection method. Okay, so stepwise will remove some of the unwanted or unimportant variables from the model while estimating. So we'll have only the most important variables, and we hope that is going to improve the model. We have few more syntax. Okay, two important keywords to remember is to have control over which variable is to be included in the model and which variable is to be not included in the model. If you don't use these two keywords and use that as part of your code, it is going to use the default values, okay, default entry criteria and stay criteria. But if you want to have control over it, you can point. So what these values are: SL entry is like what is should be the cutoff value for which would be used for an independent variable to enter into the model. And once it has entered into the model, so what is the criteria to keep it in the model? Okay, so these two are important to select a particular variable whether to be there in the model finally or not. Now, why this question comes is because in stepwise regression equation, you take stepwise approach. You do not build a logistic regression at once, just like we have done in the first case. We rather will have several such logistic regression with different set of independent variables. We'll see that in the result. So we'll first run this one. Okay, now that we have the result in front of us, so I'll straight away explain how the stepwise selection procedure works. Now, I have already said that there are several steps involved. In the first step, we do not have any variables. So the logic behind stepwise regression is that it is going to start with 0 variables, then it will add the most important variables and see if it is significant, and if it meets the selection criteria. If it meets the selection criteria, it stays, and the next important variable gets added to the equation, and then there is going to be another estimation, and then it will continue till the time we'll have all the important variables are in the model. Okay, now there are few cache. The first thing is that the entry criteria that we have mentioned should be satisfied. Okay, so it starts with step 0. It only has the intercept. So when we have intercept, it's nothing but the mean of the target variable. Okay, then in the next step, okay, the first variable li is now considered to be the most important variable out of the 6 variables. Now it enters the model. Now once it enters the model, because it has satisfied the criteria, it also stays with the model. That's what we have seen, because it is significant, right? It's less than 0.05, and it also meets the criteria for staying in the model. Now this is the criteria to stay in the model. Now internally it calculates the value, and it has found out that the p-value has to be less than 0.35 to stay in the model. Okay, and the p-value has to be less than 0.3 to enter into the model. Now both criteria have been satisfied, and this particular variable stays in the model. Okay, the second step, okay, in the step 2, so the next most important variable will be included. Okay, so which variable has been included now? So we have temp. So the second important variable is temp, which is now part of the model, and it seems to be not so significant, but we'll see whether it actually is the criteria of staying in the model is satisfied or not. It could be satisfied, so internally it evaluates, and there seems to be no effect. That means it doesn't drop out. If it doesn't satisfy that, it will drop out of the model, right? It might drop out, but it seems no effect in the model in steps 2. That means the 2 important variables that we have included so far they stay within the model, and none of them drop out because the stay criteria has been met. In the third step, the variable cell is now part of the model, and whether it stays or it drops down, okay, it doesn't drop down, so it doesn't drop up from the model, it stays in the model. Okay, and the final message that no effect made for 0.3 significant level for entry into the model. Apart from this three important variable that entered and stayed in the model, no other variable, the last three variables, did not meet the entry criteria. So a variable which did not meet the entry criteria will not be checked for stay criteria because it doesn't enter also. Only when the variable enters the model, it will be checked whether it it satisfies the stay criteria. Only if it satisfies the stay criteria, it stays in the model. Otherwise, there's no point in including these variables in the first place. So the message is clear: no additional effect made the 0.3 significant level for entry into the model. Alright, so we have finally three very important variables, and alright, so now we have the variables and the significance level. We can see one variable is significant, the other two are not so significant, but given that we have small data, we have been slightly liberal in terms of keeping the variable at even lower significance level. Okay, so first one is very significant, the other two are not very significant, but they actually help you in predicting the target variables. Okay, so we have been slightly liberal on that. Okay, and the concurrent statistics also is important. So let's see what the concurrent statistic is. So the C statistic is 0.889, which is slightly improvement from what we have seen in the plain vanilla, the first model that we built. Okay, so that's about stepwise regression model. Now, the good thing that has happened is that, so in a first case, there was not even a single variable which was significant. Now we have at least one variable which is clearly significant, and the two variables which are not significant, yet they're contributing towards predicting the target value. Okay, now we can also see other selection techniques such as backward selection and forward selection. I'll briefly talk about these two techniques. Okay, so the syntax remains same except the fact that in the selection I have used backward instead of stepwise as we have done in the previous one. Alright, so in backward technique what happens is that you start with all 6 variables and then you keep on dropping till the time your entry criteria or exit criteria is not. So we haven't mentioned any entry or exit criteria, so it is going to take the default one. Okay, so we started with 6 variables, independent variables, and we'll see in what. Okay, so in the first step, this variable blast is now removed from because it doesn't meet the stay criteria here, right? It starts with all variables. In stepwise we started with no variable and then it entered, and it could drop at any time also. In backward it starts with all variables and it slowly drops the unimportant variables. The first step, blast, gets dropped. In the second step, this variable infill got dropped. In the third step, smear got dropped, and finally I think everything else met, and the 0.35 significance level has been used while dropping them. So the stay criteria have not been made for three important variables, unimportant variable, which have been dropped out from model. Now finally you will have the your estimates as this. And you can see here also we have one significant variable and two nearly significant variable. Okay, and also need to look at the C statistics, which is same as what we had got in this stepwise regression. So finally we'll see the forward selection criteria. Well, in forward selection criteria, it's exactly the opposite of backward selection criteria. So it starts with no variable, okay, and keeps on adding. But you might wonder, how is it different from stepwise? Because stepwise also does the same. Well, in forward selection, if a variable is part of the model, or it has been entered into the model, it will never drop off. Whereas in stepwise, it can drop off at any step. Okay, so if a variable x has entered into the model, it can, in the first step, in the second step, it might drop off, because in the presence of second variable, it might not be significant, it might drop off. But in forward, once something is part of model, it is never going to drop off from the model. It is going to be there in the final model as well. So in the 3 steps, I think here also there are 3 steps, and in each step the most important variable in the order of importance gets added to the model, and I'm sure 0.3 significance level has been used to, so in backward we have only the stay criteria, the significance level for stay criteria. In forward we have significance level for entry criteria. In stepwise you have significance level both for entry as well as for stay. So stepwise is a combination of, it combines the forward and backward, and that's why it's considered better than both these two selection techniques. And as we can see, the result is more or less same, except the fact that there is slight, I rather say it's same. So so in such a case, when we have only 6 variables and 30 observation, there won't be much of a change. But if you have large set of observation, and if you see a large set of variables and you use these selection techniques, you will see a significant difference in terms of finding the most significant variables, or the best set of variables, and also in the concurrence statistics, which is going to give you an idea of how efficient your model is. And how do we select? Yes, so the important is, given the fact that we have now many selection techniques, which selection technique is to be finally used? Well, the one that is to be used should have the highest predictive ability, and that would be that you can find out by looking at the C statistics. The one that has the highest C statistics, go ahead with that. And if you have similar C statistics, look at the AIC and SC values. AIC and SC, right? That's what we have shown in this case. If you go on the top, you have AIC and SC, right? So okay, somewhere down you have AIC. Okay, here. So look at the AIC values and compare. The one that has the lowest is the one. So start with C statistics, compare. The one that has highest should be taken, and there is no question. If they're all same, then go to the AIC and SC criterion, and the one that has the lowest AIC should be used as the final model. Now finally, given the fact that stepwise regression does a good job, we'll go ahead with stepwise. And what we have done here is that we are also predicting a value, or technically we are calling that as scoring a value. So we have a model which has got 3 significant or 3 important variables in the model. So using the statistics, the beta parameters, we will score the model. So what do we get in the score? We get the probability of someone having cancer or not, right? So that's the main output we're interested in, and that will have in the data set PRED. Okay, so here against each individual patient, you have a probability value which lies between 0 and 1 of somebody completely free of cancer or not. The first candidate 0.72. So it's saying that it's likely that the candidate is free of cancer, and the actual value is 1, so that matches. That's a correct prediction. Second, it's 0.57 and it's also 1, so cutoff value that we normally take is 0.5. that means anything above 0.5 probability is considered that it is giving a value of 1. So the actual value is 1 and the predicted value is 1, so it's a correct prediction. So you look at these values and see how many times you have got correct prediction. Okay, that will give you a confidence before you can use this model in the production. That means you can use this model to score new patients, to know whether someone is completely free of cancer or not. There's also a lower limit, confidence limit, and a higher confidence limit for each one of these predicted values, so that it gives you an idea what is the bracket or what is the lower limit and upper limit of this probability value. But what's most important is this one. Okay, so we have been able to score this. Now this can well be used for new data also. Like for this data we already have the target variable, but for the new data we may not have the target variables. So by looking at this probability values and taking 0.5 as the cutoff, we can find out whether somebody is free of cancer or not. So that's a small example to understand the stepwise logistic regression, and how stepwise logistic regression is different from forward logistic regression and backward logistic regression. Thank you.